Hi everyone, and welcome to the Google I/O 2022. I'm Ivan Nardini. I'm a customer engineer at Google Cloud, and today I want to tell you a story. That story begins with you, who just joined a data science team of an important banking company. Congratulations! Now your team is part of the data office and is responsible for building innovative solutions across several business units. On day one, Maya, the product manager of the fraud detection system, has a meeting with you and your team. She shows a rules-driven engine composed of a set of if-then-else statements and logic are coded by SMEs in collaboration with software engineering team. For each transaction, she said that if it comes from the country X and the cardholder has several requests within the last hour with a certain amount, then the system assigns a fraud score of 0.95. With that, Maya has some concerns about the main challenges of the actual system. First of all, human rules are based by definition. They represent a subjective component, since different experts design rules in different ways. Secondly, the system is hard to scale because rules are required to be hard-coded. Each time a new fraud pattern is discovered by investigators, the team needs to manually express it as if-then-else statements and integrate them. Last but not least, it's also hard to maintain. Indeed, we ended up with a zoo of rules, each of them for each fraud scenario. And its maintainers are investigators and software engineers that tend to come and go, bringing with them information about how rules make the system. So because of those challenges, Maya expressed the needs of building a new system. She wants to implement a modern data-driven fraud detection engine. And because the company is going through a process of digital transformation, she asked you and your team to design it on Google Cloud. She wants a machine learning model to estimate the probability of each transaction to be a fraud. She expects that the model does not require any manual intervention. And it needs to be interpretable at the same time, in order to allow SME and investigators to validate its results and, if necessary, improve it. As I said, you are part of the team that has been assigned to design and build this system on Google Cloud. So my question is, where will you start from? Well, I'm a customer engineer, that's my job, and I spend my time talking with data science teams. And I noticed that the model and its associated technology tend to be seen as a shopping list, without considering the impact of their requirements and dependencies on the entire system. Also, it happens sometimes that phases like the model experimentation tend to drive choices about its component and how they should work. But the thing is that building machine learning models is just one phase, and it has nothing automagical. If you don't feed it with a good quality data, it will not generate good insights. And if you don't make it modular, you will not be able to adapt it when new pattern of data comes. And this is just to say that the model is important, but sometimes the big picture is missing. And when you need to productionalize your model, when you need to make it a product that will generate business value, well, the context matters most. To build it, you need culture and best practices. That's why MLOps came out. Indeed, the concept itself expresses the set of culture, practice, and technology that aim at unifying ML development with operations in order to put models into production. As Google, we were able to turn this concept concretely. For example, one of the largest production ML systems at Google has thousands of ML model training concurrently, continuously retrained with the new data every hour, and continuously deploying the global serving infrastructure. So we really know what MLOps means. And as Google Cloud, we want to share those expertise and technology with you. About the expertise, you have people like me that are ready to support you in your ML journey day by day. But talking about technology, that's the reason why we launched Vertex AI, which is the Google Cloud managed machine learning platform to help you accelerate experimentation and deployment of ML models at scale. All you need to know is that the platform has several building blocks that allow you to cover the entire lifecycle from data ingestion to model training all the way down to model prediction and model monitoring in order to productionalize your models. So now that you have the technology, the next question is, what would be building the new fraud detection system on Vertex AI? what would it look like? How would it be better compared to what you have? Well, I already know the answer to those questions. Why? Because I did it. In collaboration with some of my colleagues at Google Cloud, we built Fraud Finder. Fraud Finder is a project that comes from some customer needs to apply the state-of-the-art of data science and machine learning to detect fraudulent transactions at scale in real time. It's still a work in progress, but me and the team learned so many things along the road that we thought, why don't share our experience? So here I am. Are you with me? Let's go on. To build a simple fraud detection system as Fraud Finder, you start from data of historical transactions. Just to clarify, in your case, a transaction is an event recorded at 5 a.m. today associated with a customer with a particular ID who made a payment of a certain amount to an identified merchant. Now, part of that information cannot be consumed either by a model as they are. In fact, the model needs numbers, and only some of them are numericals. Also, you can think of applying several data transformation techniques to derive new variables which will be relevant to predict if a transaction is a fraud or not. Will the number of transaction customers make recently matter? What about the average transaction amount in the last week? Could the terminal be compromised for any customer who is using it? In other terms, you define a set of features to identify customer spending behavior and characterize the risk of fraud associated with the terminals over different time windows. And you can do that by using BigQuery, which allows you to analyze terabytes of data per second. At that time, you get your features, and you are ready to train your model. But let's consider some aspects for a second. First of all, in a real-time fraud detection system, some of these features cannot be calculated on the fly when you serve the model. How would you get the average amount of transactions over the last 3 days in milliseconds? You need a way to pass them as inputs to the model if you want to generate online predictions. Now, BigQuery is not engineered for low latency reads. That's why you need to introduce an optimized data store for lookup operation at scale in low latency. But there is another aspect that needs to be highlighted. In that real-time system, you have a high volume of transactions you can use to calculate those features we keep floating and collected constantly over time. It implies that you always get fresh data to reconstruct features, and depending on when you decide to calculate one feature or another, you can end up with a set of features that are not aligned in time. For example, you can keep calculating the number of transactions over the last 3 days, each day at midnight, but at the same time, you will need to calculate the average amount of transactions over the last 3 hours along the day several times. And as you can imagine, this has implications when you need to train your model. Indeed, when labels become available, those features will not be aligned with them as well. In your case, you will know if a transaction is a fraud or not only after some time. The investigation is run and validated your predictions. Because of that, it sounds incredibly difficult to say which set of features contain the most up-to-date historical information associated with the label you want to predict. And when you're not able to guarantee that, the performance of your model would badly affect because you serve no representative features of the data and the label from the field when the model goes live. So you need a way to get the most up-to-date feature you calculate over time before the labels becomes available. In other terms, you need a time travel machine for your features with respect to your labels. For all those reasons I just mentioned, you may decide to introduce a feature store, which provides you a service that helps you to address data leakage by providing point-in-time lookups, which fetch the most up-to-date features with respect of the time labels become available. And at the same time, it serves those features at scale with low latency as they were available at training time, mitigating the way possible training and service queue. So once you ingest the features into the feature store, you are ready to train your model offline. You fetch a sample of them aligned with the label into a notebook environment. You use this sample for running experiments by defining different training configuration and tracking model evaluation metrics. And once you find the best modeling approach, you formalize the model training as a pipeline component. Then you easily integrate that component in a machine learning pipelines that allow you to cover all the steps required to reproduce the model training at scale. And if and only if the model achieves certain threshold levels in performance metrics, then it goes deployed to serving environment for generating online prediction when a new request will require. Notice how the feature store passes the same aggregated features you have calculated offline to train the model to produce online predictions. In other terms, it solved the training service queue I mentioned so far. All I showed you until now, from feature store to model training with pipelines and the model serving, can be implemented on Vertex AI, which provides you all those capabilities by letting you keep focusing on your code and improving the quality of your solution. And talking about the solution, let me show you what we got. This is Fraud Finder, the data application we worked on. Once you pass some parameters such as the feature store resource name and the endpoint ID, you can start streaming the transactions that are generated for a data synthesizer we built in the backend. After a while, if you go in the predict view, you can see in yellow the transactions that were classified as a fraudulent with respect to a particular probability threshold. And if you change it, you can verify that the frauds become less frequent. Lastly, under the dashboard view, you have the profile of latency, which is represented by the distribution of prediction requests over a fraction of a second. As you can see, the backend is doing a good job. If you consider that per each request, it reads features from the Vertex AI feature store. It passes them into Vertex AI endpoint with transaction amount and other variables from the field, and the model generates prediction and return them back. All this thanks to Vertex AI. About the rest, you also have the distribution plot of the fraudulent and non-fraudulent transaction, and you also have some views showing the active endpoints and the model we have on Vertex AI. Okay, this was just an example of what you can achieve by leveraging Vertex AI for MLOps. We are at the end of this journey. To conclude, you start from a system that it has bias because rules were written by SMEs based on their knowledge. It was hard to scale because rules required to be hard-coded. It was hard to maintain because of the zoo of rules it generates. And today I show you how you can solve those challenges with a simple fraud detection system which leverages both data to train machine learning models and Vertex AI platform to productionalize them. So now that you know that this is possible, it's your turn. Open the console and start building and putting your models into production using Vertex AI on Google Cloud. But don't forget one thing. All I presented today was possible because different people with different skills and backgrounds decide to join, work together, and learn from each other as a team. This is just to say that machine learning is a part of the picture, and MLOps is about culture, practice, technology, but more importantly, people. I hope you enjoyed the session. Thank you, and see you soon.